The last topic of this chapter is parallelism. Parallelism is another form of sequential logic. Two types of parallelism exist, spatial and temporal. In spatial parallelism, we duplicate hardware. So for example, we have two adders and we can perform two additions at the same time in parallel. Temporal parallelism is like, it's like an assembly line where we break a single task up into multiple stages. So this is called pipelining, but again, the kind of more common everyday example is an assembly line. Let's look at these two options of parallelism. First of all, we're going to talk in terms of a token or a group of inputs being processed to produce a group of outputs. Latency is a time for one token to pass from the start of a computation to the end. And the throughput is the number of tokens produced per unit time. Parallelism increases throughput, but it doesn't decrease latency. So let's do an example. Let's suppose Ben Bitdiddle is making cookies to celebrate the traffic light controller installation. It takes him 5 minutes to roll the cookies and 15 minutes to bake them. So what is the latency and throughput? Latency is just the time it takes to process a single token or a tray. So 5 plus 15 minutes or 20 minutes. And the throughput is 1 over that. So 1 tray per 1/3 of an hour. So it's equal to 3 trays per hour. So that's the throughput, how many trays he can process in an hour. So now let's suppose Ben decides to use parallelism. We can consider both spatial parallelism, he asks his friend Alyssa to help him, or temporal parallelism where he uses 2 stages to roll and bake the cookies. And he's going to need 2 trays because while 1 tray is in the oven, he's going to be rolling the next tray. So with spatial parallelism, we have 2 kind of paths running in parallel. So the latency to, if you're like, I really want those cookies and you roll them and put them in the oven and bake them, well, you still have to wait the same amount of time. You still have to wait 5 minutes plus 15. So the latency to, eat your first cookie is still 20 minutes. What about the throughput, though? So the throughput, in this case, we have 2 trays being produced every third of the hour, every third of an hour. So 2 trays every 1/3 of an hour. So we're going to get 6 trays per hour. So as expected, by having 2 paths, now we double the throughput. The latency, you're super hungry for that cookie, still have to wait your 20 minutes. But the throughput just doubled. Instead of 3 trays per hour, we're going to get 6 trays per hour. Now Ben decides to use temporal parallelism. So he's going to roll a tray of cookies and then put the tray in the oven. But while he's waiting for that tray of cookies to come out of the oven, he's going to roll the next tray of cookies. So the latency from when he first starts to getting his first cookie out, the latency is still 5 plus 15 minutes or 20 minutes. But let's think about the throughput. So after the first batch of cookies, he's going to be getting out a new tray of cookies every 15 minutes. And so the throughput is 1 tray for 15 minutes, well, 1/4 of an hour, every 1/4 of an hour. That's going to be 4 trays of cookies per hour. Now, if we employed both methods, temporal and spatial parallelism, so he and Alyssa both use temporal parallelism, the throughput would be 8 trays per hour.